In this video, we are doing another Nastran Solution 200 tutorial. We are going to focus on something called model matching. Some refer to this as system identification. Others will call this to results correlation. So what is our goal in this example? Here we have a very simple beam, if you will. One end is fixed while the other end is allowed to freely move, if you will. And we've performed a finite element simulation that you see here represented in orange. Here in orange is the first bending mode. And now here in blue, we've taken the same finite element model and we've performed a physical experiment on something comparable. Here in blue, we have our experimental results. And here the challenge is that our finite element solution is not correlating with experiment. So our goal is to address this discrepancy. What we are going to do is we're going to allow one of the dimensions in the model varying. Here you can see the dimension here is the radius of the cross section in the yellow section. We're going to let this radius vary so that was the mode shape that was previously represented by orange becomes a new mode shape represented in gray. And our goal is to make sure that this mode shape aligns with the experimental result. So here you can see the gray or optimized mode shape is in line with the blue points, which are the experimental points. And so what is it going to take to get to that point? I'm going to detail how to set this up for Nastran Solution 200. I'll first need to talk about the optimization problem statement. I'll then discuss how to convert a BDF file to Solution 200. I'll perform the optimization, and then we are going to explore the results at the end just to confirm our new mode shapes are correlating to the experiment. And then at the end, I'll show you how to update your original structure with the optimized parameters. Just in case you are a professional engineer and would like personal or more advanced training, you can contact me at this email address and I would definitely get back to you. Now, if you are a student or professional engineer and would like free access to the Nastran Solution 200 web app, this web app is what makes it possible to perform optimization. You can also contact me at this email address. I first saw this example in the UAI Nastran Users Guide. This guide must be possibly 15 or 20 years old, but this example is really good that demonstrates how to perform model matching with Nastran Solution 200. So here I just have the citation just in case you're interested. Here again, we have a very simple beam. One beam is fixed. There are a few elements that represent the finite element model, and the other end is free to move. Here are some other properties of the model. This table is a summary of our experimental values. Here for mode 1, we measured the experiment or the prototype, if you will, at 3 different points. We measured it at node 3, node 6, and node 9. So here you can imagine this is a node 3, node 6, and node 9. And these are the experimental values that we should be getting. We did the same thing for mode 3. And here the one key takeaway is that here in orange is our finite element solution, whereas in blue is our experimental solution. This discrepancy, this difference is what we want to minimize with Nastran Solution 200. So now what are we going to vary? Our design variables are the first piece of the optimization problem statement. Here, zone yellow, if you will, is represented by radius 1, and zone green has a different radius I will call radius 2. Radius 1 of the yellow section is what we are going to vary. So this I'm going to label design variable x1. We are going to let the radius vary between 0.1 and 10. And now here so far we've defined the first piece, which is the design variables. Now let's talk about our objective and constraints. Our objective, or rather, this finite element model is going to generate a lot of outputs. You're going to get natural frequencies, you're going to get various mode shapes, and there are so many other quantities you're going to get. It's up to you to decide out of all of these quantities what you want to minimize for the objective, and for the constraints, what limits or what outputs do you want to limit for the constraints. Let's talk about the objective for a moment. We are going to take the root sum of squares of the various discrepancies, and we are going to minimize that value as much as possible. So think of this as the error in between the experiment and the finite element model. We want to minimize the error. So here what we are going to do is define a term called A1, A2, and A3. A1 represents the relative displacement for mode 1 at node 3. A2 represents the relative displacement at node 6 for mode 1, and here the same for node 9. Then we are going to take the difference between the experiment and the finite element value, and we are going to repeat the process here for term B and C. We're going to take again the root sum of squares, and we are going to minimize this. We are going to do something for the design constraint. We want to do something comparable for mode 3. Unfortunately, you can only set one value as the objective. So here in the previous slide we are focusing on mode 1 here, the RSS value called R0. But for the constraint, we are going to define the root sum of square for mode 3, but instead we are going to use a tolerance value. We are going to say that this value should be no more than 0.002. And again, we're going to define terms B1, B2, and B3 that represent the various values of the mode shape of the finite element solution. And then we're going to take a very similar expression like the objective here and constrain it to within a value. One very important thing we should discuss, mode tracking. The design constraint that we've defined will be applied to mode 3. Now, we're dealing with the computer algorithm, and each algorithm is very literal. If we assign the constraint to mode 3, watch what could happen. Here, mode 3 has a natural frequency of 263 hertz, and it has this mode shape, which is extensional. So the mode shape, you can imagine, is going in and out down the length of the structural member. Now, let's suppose the natural frequency of this mode shape increases. Here on the right is that scenario. Here on the left, we had a radius of 2, but then the radius becomes 3.9. What happens to the mode shape and the natural frequency? Here, if we look at mode shape 3, you see the mode shape is now almost a flexural or bending mode shape. What happened here is that what was once 263 hertz has now increased to 334 hertz. And the way I know that is because the mode shape for mode 4 is now extensional. So this means that what was once mode shape 3 has become mode 4. But if we apply the constraint to mode 3, Nastran, being very literal, will still apply the constraint to mode 3. And this is not something we want. Nastran has a feature called mode tracking. So think of it as tracking, say, perhaps the mode shape. If it detects that the mode number is incorrect, then it will use some information about the natural frequency and the mode shape to decide if the constraint should then be applied to a different mode number. So I'll detail how to set this up in a moment. And here, just a snapshot of the entire problem statement. Again, you want to have this ready to go before you start setting your problem up. So now let's go ahead and talk about the procedure. So let me move this to the left. And let me minimize everything else and talk about what we should have. In the video description below, there is a link to a PDF file. Feel free to download a local copy of your own PDF file and follow along with the tutorial. This PDF file could have been generated from your pre-post processor. Here, I've already taken the time to go ahead and define my finite element model. I've already performed my normal modes analysis, so I know this model is functional. Here on my desktop is the starting point. What I want to do now is use the web app to perform the conversion process. Again, it's going to take your PDF file. It's going to let you define your variables, your constraints, and your objective. And it's going to let you convert it to solution 200. So now let's go through that procedure. So let me minimize this and open the web app. Let's go ahead and select this BDF file. The BDF file can also be a DAT or DAT file. Here, once you upload it, the web app identifies all the properties that can be set as design variables. I can set the Young's modulus, the density as design variables. I can set radius 1 as a design variable. I can set radius 2 as a design variable. Here, let me go ahead and click on the plus icon for radius 1 or dimension 1 of p bar L1. And here I have my newly created design variable called x1. Let's go ahead and look at the problem statement. And here I see that the range of values for the variables is 0.1 and 10. So here, let's go ahead and type in 0.1 and 10 here. And so the radius will be allowed to vary between 0.1 and 10. Here on the right, I have my necessary entries for the design variable created for me. These are updated for you instantly. So here, if I wanted to change the upper limit to 20, here on the right, you can see that the upper limit has instantly been changed for you. So here, let me change this back to 10. And now let's go ahead and go to the objective. Here's a long list of set values you can set as objectives. But here we want to create a custom equation. So for this, let's go ahead and jump and click on switch to equation objective. The first thing you want to do is define your A1, A2, and A3 terms. Remember that those terms correspond to these points. So here, let me zoom out a little and show you this plot. So A1 represents this point, A2 represents this point, and A3 represents this point. This orange curve represents the mode shape of the finite element model solution. So let's go ahead and create one point. So here the label is A1. I want to track the relative displacement in the z or third direction of mode 1, I believe. And here, let me check the optimization problem statement just to make sure I'm following this correctly. Mode 1, yep, that's correct. So here, let's go ahead and type in 3. And now let's repeat the process, A2, A3. So here you see these two new responses are created for me. I'll repeat the process. I want to track the third component of displacement for mode 1. But then this is for node 6 and node 9. So I've defined A1, A2, and A3, which corresponds to these 3 points here. So that would be, it's a little tough here with PowerPoint. So this is A1, A2, and A3. Now let's move on with the optimization problem statement. I need to define this equation here. So here I'm taking the root sum of squares for the differences between the experiment and the finite element solution. So here, let's type in this first term here and scroll up a little. And this is where I can type in my equation. So here I'll type in the square root of, here, let me look at my notes, 0.0143, which is the experimental value. And then here I'll type in A1 squared, close. And so we need to repeat this process. So we'll go ahead and type in plus 0.071741 minus A2 squared plus 0.6381 minus A3 squared. So this is the expression for the objective. Our goal is to minimize this objective. Here for node 3, we are saying take the difference between the experiment and the finite element solution, square, and then repeat the process and add it to node 6 and node 9. This completes the creation of the objective. Make sure to triple check this expression. I've done this example numerous times, and very often I forget to include a decimal or I mistype one of these numbers and it throws my solution totally off. So make sure to triple check these values when you type them in, and you should do this whenever you type in an equation. Let's go ahead and move on to the constraints. So here, as always, you have a long list of quantities you can set as constraints, but here we want to create a custom equation here. And here we can type in the square root expression. And now we first need to define our three terms for mode shape 3. So here what we are going to define, and this will probably be a good thing if I use a highlighter. This point here will be defined by B1. This point here will be defined by B2. And then this point here will be defined by B3. So let's go ahead and define these three terms right now. So we'll go ahead and click on the plus icon here for other responses. These responses are used to identify single values from your output. So here I'm going to select the first component of mode 3 for node 3, and we'll go ahead and repeat the process. First component of relative displacement for mode shape 3 for node 6, node 9, and now if I scroll up 3, those terms A1 or B1, B2, and B3 are available for the equation. So let's go ahead and type in our equation here, 0.1204 minus B1 close plus 0.5431 minus B2 close. And here the double asterisk represents I'm taking the square. And then here let's type in our next value, 9216 minus B3 squared, and close it. So as always, triple check your equation. Make sure you have 0.1204 here, 0.5431 here, and 0.9216 here. And then for the tolerance value, or the upper bound, this will be 0.002. Now let me go back to the objective and make sure this equation is properly typed in. Again, I've done this example numerous times. Every now and then I accidentally mistype a number and that throws my solution off, so that's why I'm triple checking this. So my constraints, everything looks good. And now let's go ahead and move on to the exporter. And let's go ahead and download local copies of these files. Remember, once you export a file from, say, Patran, you'll have a BDAF or DAT file. This DAT file is what has to be converted by the web app. When you hit download here and here, this downloads converted versions of that BDAF file. So here on my downloads directory, I have the new files, and the second file contains information about the design variables, the objective, and the constraints. So now what I can do is start Nastran and perform this optimization. So let me go ahead and run this. And then after the optimization is complete, open the F06 file and scroll to the very bottom of the file. And one thing I forgot to do is I forgot to include information regarding mode tracking. So let's go ahead and take a step back and delete all of our old files. And let's go into the model PDF file. And close everything else. Go up here to the case control section. This is the section between the C end marker and the begin bulk marker. This is the case control section. Here under subcase 1001, go to a new line and say mod track equals 800. So this is saying use the tracking point. This is a pointer. Point to mode tracking configuration with ID number 800. Here in the bulk data section, and this is the section after begin bulk, type in mod track, comma 800. So this is mode tracking identification 800, and type in these values 1 and 100. Now let's go ahead and perform the optimization after you save the file and click run. So just in case you have comments regarding mode tracking, feel free to send me an email and I will get back to you. And like before, after the optimization, let's go ahead and investigate the F06 file. Go to the very bottom and look at this message. Run terminated due to hard convergence. This is indication that your model has been successfully optimized. So now let's go ahead and look at some of these quantities. Here in the web app, click on plots. During your optimization, a CSV file has been created for you. You can upload the CSV file and view the change in your objective and your design variable. So here we see that the root sum of square value for the objective started at 0.197, and it ultimately went down to a value very close to 0. That's very good for us. And here I should actually show you what does this mean. Here in yellow, or here in red, remember the orange line is the original mode shape. Here in gray, so that'll be this gray number here, this gray plot, this is the new mode shape of this new optimized design. And you can see that the gray finite element mode shape is in line with the blue experimental points. That's why the objective now has a value very close to 0. In essence, the discrepancy has been minimized. Now, if we do the same thing for mode 3, you'll find something very similar. And here, I'll feel free to pause the video and explore the plot here on your own. Let me go back to the tool here. And now, what about the variable? Remember, we decided to vary the radius of the cross-section. So here we started at a radius of 2. The optimizer ultimately landed on a value of 3.93 for the new radius. One other thing you want to do, in addition to checking this history of the optimization, look at your results in your pre-post processor. So let's go ahead and do that now. If you go to analysis and click on attach a result file, for you it might be an OP2 file, it might be an XDB file, it could be something else. The important thing is you bring those results into your pre-post processor. Here I am using Patran, and confirm the results. I've done this in the past where I've misconfigured my constraint. Say I wanted to constrain displacement and I picked the wrong direction. When you visually inspect the results, that can visually show you if something is off. So here, let's go ahead and look at the first mode shape, if you will. So here, I'll click on deformation. Here, I have a lot of data. One thing you'll notice is that you have 2 sets of data. Here, I have 4 mode shapes for marker D0. D0 is the first initial design. D4 is the final design. These D markers are also used in the plotter. So here, initial design is D0, D1 for the first design cycle, D2, D3, and D4. Instead of writing D4 here, it's just called the final design. So here, this first set of data are the mode shapes for the first, original design. So here, let me orient this here. So here's the first mode shape. And then here, if I switch to D4 mode 1, I have the new mode shape. And then I can show you what the mode shape is for mode 3. Mode 3 is an extensional mode shape. So you can see it would be moving left and right here as you see that. And let's go ahead and look at mode shape 3 here again for the new design. So you can see that. So there you have it. That is how you use Nastran Solution 200 for model correlation or results correlation. It's alternatively known as model matching and system identification. Now, one last thing I want to go over. This original BDF file has old data for the radius. If we open this and we go to pbar L1, so pbar L with ID 1, it has the old radius of 2. We have to update this now, so let's go ahead and describe what the procedure is for that. In your downloads directory where you perform the optimization, there is a new file called PCH or punch file. If you open this up, you'll see that it has a new P-bar-L1 entry. So P-bar-L here with identification number 1. What you can do now is copy this P-bar-L1 entry and replace the old P-bar-L entry in your BDF file. And here what I should do is I should make a copy. So here on the right is my new copy. So let me open the copy. So here on the right is my copy. I'm going to copy what I have here on the left, and I'll replace what's here on the right. So now the file on the right has the latest radius for the cross section. So let me go ahead and save this. And this file on the right has been updated with the new optimized dimension for the cross section radius. If you were to perform an analysis using this BDF file now, you should obtain the same results that we reviewed a moment ago for design cycle D4. So that would be this one here. So there you have it. That is how you do this. Let me go ahead and make my final last comment. Again, if you are a professional engineer and you would like guidance on how to do this on your end, you can contact me at this email address. Also, would be more than glad to sit down with you and go through some more advanced training. If you are a student or professional engineer, you can also contact me for access to the Nastran Solution 200 web app. As you saw, it can generate a lot of the entries for you very quickly and correctly. So again, if you are a student or professional engineer, you can get free access to the web app by sending me an email. With that, I think I will stop there. And as always, thank you for watching.